This is 4.3 Transformations Day 1. We are looking at graphs and how they transform from their original parent function. Now, if you look at your note packet, the page before this page, I don't know why mine moved, but that's okay. You have a parent function page. So it goes through all of the different parent functions that you have, and you'll be able to look at that and help you identify your parent functions. All right, so let's start looking at our transformations. Some things to remember: is it with x, then it's happening in the x direction or horizontal. Not with x, then it's happening in the y direction and it's vertical. X is our little backwards. We need to do the opposite of what it says to do. So we're trying to get back to where it's just f of x. So that's why we're doing it backwards. We're trying to get the things that are with x away from x to get it so it's like the parent function. This is our basic equation for transformations. So we're going to go over each letter and what each of them do. First up, we have reflections. So our a of our equation, if it's negative, so when a is negative, it's going to reflect across the x-axis. If b is negative, it's going to reflect across the y-axis. And we'll look at the graphs later and see what that looks like. Next, we have our vertical stretch and shrink. So that is going to be our a value because it's outside of our f of x. So it is going to be a vertical transformation. A vertical stretch is going to be when the absolute value of a is greater than 1. So like 2, 3, 4, 5, 6, any number like that, it will be a vertical stretch. And it will only affect the y values. A vertical shrink is when a is in between 0 and 1. So 0 less than a, and it's the absolute value as well because we're ignoring the negative when we are looking at our a value. So an example of that would be like your 1/2, 0.5, 3/4. So any number that's less than 1 but bigger than 0. And that also only affects the y values as well because it's a vertical stretch or shrink. Vertical shift up or down. So remember, these are only affecting our y values. And that is our d in our equation. So when d is positive, it's going to shift up. When d is negative, it will shift down. Horizontal stretch or shrink, that is going to be our b value because it is now inside with x. So same as like the vertical stretch or shrink, it's between 0 and 1 and bigger than 1. But remember, our x's are backwards. So a horizontal stretch is between 0 and 1. I'm going to do it a capital B because my B's look like 6's. So B and 1. A horizontal shrink is when B is greater than 1. And it's the absolute value. Because our x's are backwards, when you're looking at your horizontal stretch or shrink, it's going to be 1 over b. So whenever you're looking at your b value and seeing if you have a horizontal stretch or shrink, you are going to do the reciprocal of that number. So you are going to flip it upside down. And we'll take a look at examples of that later on. Next, we're looking at horizontal shift right or left, and that is our last letter, C. And notice how it's inside with X. That means it's going to be opposite of what we think. Shifting right is going to be when C is negative. Shifting left is going to be when C is positive. Now the reason for that is that when we are solving for X, we move the things to the other side. For example, X minus C equals 0. We're going to add C to make it X equals C. When we have X plus C, we are going to subtract C. So remember they're opposite. Just like when we were doing our zeros in Unit 2, we changed the sign. That is because when we are looking at our graphs, we're trying to get back to where X is alone. That means we have to solve for X and get it by itself. So we are changing those signs. Here we have a table of all of the different transformations and what they do to the points of the graph. So if you want to pause the video here and look at all those examples, you can. If not, we're going to continue and look at different examples and how the graphs are shifted. But this shows a nice representation of changing your points when our D value, we're adding it to the Y, C value, we're adding, subtracting to the X value, reflections, depending on which axis they're flipping, would happen to the Y or X value, not both. And your A value happens to the Y value only, and your B value only happens to the X value. It gives that nice representation. All right, let's look at our examples. Here we have g of x is equal to f of x plus 3. Notice the dotted line on your graph. That is your parent function. This is an x to the third function, or a cubic function, and it goes through 0, 0. We are looking, when we're looking at transformations, we're looking at the center of the graph where we are shifting. Trying to change my pen color here. So we're looking at that center. So if we are adding 3, that is our D value. So we're going up 3. So 1, 2, 3. So it's only affecting the Y value. It's not affecting right or left. It's only affecting the Y value. If we had an XY chart here, this is g of x. So it's 0, 0, and then, this is f of x, and then g of x, we would be 0, and then 0 plus 3, because we're shifting up 3. We're only changing the Y value. All right, let's look at h of x and graph it. So it says we want to subtract 2. So looking at those points again, 0 and 0, we're going to minus 2. So that means we're going to be at 0, negative 2. So going down. And then we need to know the rest of our points here. So looking at our dotted line graph, our parent function, we want to find maybe 2 or 3 other points just to find more points that have shifted. So we have 1, 1, and then negative 1, negative 1. So remember, we are only changing the y values. So 1 and 1 minus 2, that's going to be negative 1. So still at 1 on the x, but we're going to be at negative 1 on the y. Next we have negative 1, and then we're going to subtract 2, so we get negative 3. So at negative 1, negative 3, we are at that point. So then we can kind of sketch our graph from there, and it shifted down those 3. Let's look at our horizontal shift, our left or right shift. Looking at this first one, so we have our dotted line again, that's our parent function. This is our absolute value of x for our parent function. Again, we're at 0, 0 for the center of our graph. And then we are going to be shifting our x values in the opposite direction. So notice x plus 2, we went to the left 2. So g of x, so 0, minus 2, and 0. So it still stays the same on the y. You could also look at our points. So we have 1, 1, and negative 1, 1. So we would also subtract 2 for those. But our y values would stay the same. So negative 2, this would be negative 1, this would be negative 3. So notice how those shifted over. All right, let's look at h of x. That's supposed to be h of x, not g of x. This time we're subtracting 4, so x is going to equal 4, and this one was a negative 2. Because remember, we subtract, and then this one we're adding. So we're doing that opposite to get back to that parent function. All right, so for our first point, 0, and we're going to add 4. So 0 plus 4 is going to be 4. Next one, we have 1 and 1 plus 4. So that's going to be 5. And then 1 and negative 1 plus 4, that's going to be 3. All right, let's plot those. So 0, 4, or 4, 0 is going to be here. And then we have 5, 1, and 3, 1. And then you sketch it to match your parent function. All right, let's look at our next one. We are doing a vertical stretch and shrink. This is a sine graph. So this is sine of x. If you're looking at your parent functions, we'll look at our sine graphs and cosine graphs and tangent graphs when we get to our trig units. But as far as transformations go, you're just looking at the x and y points and adding, subtracting, multiplying, all of that. So we can look at the points instead of the actual graph itself. All right, the dotted line is our parent function. So we have our x and our y. So for our f of x. So it's 0, 0 again. And let's pick some other points while we are here. All right, so these halfway points here, see this is pi and 2 pi, negative pi and negative 2 pi. Well, these points right here, these are pi over 2 or 0.5 pi. All right. We are going to be doing the vertical stretch. So we have our first point here. from here to here, we have pi halves and 1, and then over here we have negative pi halves and negative 1. For g of x, we are multiplying our y values by 3 because it's a vertical stretch, so we're affecting our y values. So for 0, 0, 0 times 3 is still 0. So when we have that vertical stretch or shrink, it usually doesn't change the position if we don't have any other transformations added on. It will stay in the origin or that 0, 0. All right, next one. So we have pi halves. And then 1 times 3 is going to be 3. So 1, 2, 3. So notice it's right there. Negative pi halves. Same thing, 1 times 3, or negative 1 times 3 is negative 3. So let's check that one. 1, 2, 3. And we are right there. Let's look at h of x. So that was going to be a stretch because 3 is greater than 1. So remember, our stretch or shrinks, if the number is bigger than 1, it's a stretch. Between 0 and 1, like a fraction, would be a shrink. So like this next one, that 1/3 is going to be a shrink. So we are going to be multiplying our y values by 1/3. So 0, pi halves, and negative pi halves. And you don't have to have these memorized on your assignments and things you won't have, like your sine and cosine graph. This is just to show you what a stretch and shrink is like. So don't worry so much about, oh, I need to know what the pi halves and negative pi halves is. You don't necessarily. Usually your graphs will be labeled for you and you can determine from there. All right, so 0 times 1/3 is still 0. 1 times 1/3 is going to be 1/3, and then negative 1 times 1/3 is going to be a negative 1/3. So notice when we had g of x, it stretched it and made those points longer and more away from each other. Let's see what the shrink does. So we're at 0, 0, and then at pi halves, we're at 1/3. So that's going to be kind of close to 0. Same thing with that. And if you sketched it, it would kind of look like this. We are flattening that curve, which is shrinking those y values closer to the x-axis. Instead of spreading them more apart like on the blue graph, it brings them closer together, so it's flattening or shrinking that curve or that graph. It doesn't affect your x values, it only affects your y values and how far away your points are going to be from each other. All right, next we have horizontal stretch or shrink. This is going to be on a cosine x graph. And we are at 0, 1 this time for our origin. It's one of the few parent functions that has a different starting point other than 0, 0. There are a couple of other ones, but this is just one of them. I keep doing that. F of x. So our point here is 0, 1. And then the next points we're going to be looking at is our 0.5 and negative 0.5 pi points, or our pi halves and negative pi half points. So 0.5 pi and 0, and negative 0.5 pi and 0. For g of x, we are going to be multiplying by 2 in the horizontal. Now remember, with our horizontal stretches or shrinks, we are doing 1 over b. So we're actually going to be multiplying by that reciprocal. And it's our x values that we are going to be multiplying by. All right, so 0 times 1 over 2 is still 0. So notice that point didn't change on that blue graph. And then next one we have 0.5 times 1/2 and we are going to get 1/4 pi. My equals to sign is in the way because the pi has to be next to the 1/4 and not with the 4 in the denominator. There we go. Because 0.5 is the same as 1/2, if you have 1/2 times 1/2, you are going to get 1 over 4. So that's why it's 1/4 when we multiply 0.5 and 1/2 together. All right, next one, negative 1 over 4 pi. Because it's that same thing, 1/2 times a negative 0.5 pi. And we'll just move those points, and that's going to be at 0 as well. It's not affecting our zeros in any way, or our y values, I should say. All right, so notice on the blue graph, these move to this point here, which is that 1/4 pi point. So it just brought those x values closer together. So it's going to be a shrink. So it's shrinking those x values, is bringing them closer together. So that's making them, that's why it's called a shrink. It's bringing those x values closer together and the distance is being shrunken. All right. Next we have h of x, and we are doing a 1/2. So that means we are going to be multiplying by 2 because the reciprocal is 2 over 1. So that's just 2. H of x, x and y. So we have 0, 1. 0 times 2 is still 0. And then next one we have our 0.5 pi and 0 and negative 0.5 pi and 0. So we multiply those by 2. And 2 times 0.5, or 2 times 1/2, is going to be 1. So these are going to be 1 pi, or just pi, and negative pi, because they're the same number. All right, let's look at the graph and graph those points. We have 0, 1, so that same middle value, and then we have 0 and pi. Notice pi is way over here, and then negative pi is going to be way over there. All right, so we connect those points, and it's kind of, we match that same like curvature. These look weird. All right, so notice it stretched those x values farther apart from each other, so they're more wide apart. So that's why when it's a 1/2 or that 1 over b, we're going to flip it, and it does the opposite. So this is a stretch, and this is a shrink. So when it's that horizontal stretch or shrink, it's going to move your points either closer to the y-axis on the x-axis. So moving them closer together on that x-axis or farther apart depending on your stretch or shrink. And then if it's a vertical stretch or shrink, vertical stretches, they're moving away from the x-axis, so it's kind of like that opposite. And then a shrink is going to bring them closer to the x-axis. So just notice those for the x and y values. All right, next up is our reflections. These are just going to show you that what they look like because they just flip across either axis. All right, we're looking at a parent function of a square root of x, and we notice that it starts at 0, 0. And the reflection, if it's on the inside, it's going to reflect across the y-axis. So we can look at points and see why that's the case. All right, so we have f of x. So we have 0, 0, 1, 1, and let's do 4, 2 as well. Because it is a square root, we want to get nice whole numbers there. All right, g of x, if we're applying that negative to our x values, so negative 0, which is just 0. And then we have 1 and 1. Well, if we do our negative times that 1, it's a negative. We can't square root a negative 1. Remember, that's an I. So we have to look at the domain for those. So when we are flipping it, it's going to be on the other side. So we will have to change these to negative numbers instead. So negative 1 times a negative is going to be a positive 1. And then we have negative, negative 4. So that's going to be at 2, because it's going to be a positive 4. So just know that if it's a square root function, it's going to behave a little bit differently because of those restrictions with our square roots. All right. Let's look at a reflection on the x-axis. So that means the negative is on the outside, and it's going to affect our y values. So still looking at square root of x. So we have our 0, 0, 1, 1, and 4, 2. And notice when it's on the outside, we don't need to worry about our domain restrictions because it's affecting our y values and not what's inside with x. All right, so we have 0, 0, and then 1, and then we're going to do a negative square root of 1. So the negative is on the outside. So that's going to be negative 1. And then if we do 4, so negative square root of 4 is going to be negative 2 because the negative is on the outside. So notice how it flips that there. So x-axis reflect is going to affect your y values.